Hello students. Today we'll continue again with the fourth module. In this we'll study about the design challenges, design abstraction, design hierarchy, physical design of FPGA. Under that we'll discuss about the placement and routing. Coming to the goals, when we have to design the IC, there are certain performance characteristics or design metrics which has to be considered, like the performance of the IC, whether it is able to perform or give an output for what it is designed for, the power consumed and the heat it dissipates, and if it is a battery output operated, what is the power consumed, then heat dissipation, what are the heat sinks, how are we going to provide a heat sink, so even that will cost us, and the design time, the design cost and manufacturing cost. And then we are talking about heat, there are a lot of things that come into picture, the conductor, the heat sinks and the placement, delay, everything, current. So there are so many things which will have to be taken care of. So next is the design abstraction. Design abstraction is how we are going to break down the given specification or a given design and then start designing. Basically, there are two types. It is the top-down and bottom-up approach. In top-down approach, we go from the top and go to the bottom level. That is, for example, it is the system level. Suppose the user is giving a specification or some his requirement. That would be called as a system level specification. He tells his requirement. Based on the requirement, in the next level, that is a behavioral level specification, for the specification received, an algorithm, a flow chart, or a truth table would be written. So from the truth table, the next level, that is you write a FSM or we derive an equation. We know from a truth table, based on the K-map, we can get an equation like y equal to a into b or a plus b or some like complex equations we get. Then we know that is a plus b means it has to be an OR gate. A into b is a NAND gate. So a AND gate. So based on this, the next level comes, that is a gate level, knowing what gate has to be used. And we know that transistors are involved in designing gates, and also we know if it is an AND gate, it has to be in parallel, nor it has to be in series. So how we are going to design these gates using transistors? So that is, we starting from the top, using the specification, we break it down in each level and finally reach the bottom level, and from the bottom level the design starts. So that is called top down approach. We break down into the basic level and start designing. Bottom approach will be using what, that is from the transistor we go up, that is the bottom up approach. Next is design hierarchy, that is in the same level, abstraction level, either in the behavioral or in RT level or in the gate level. The modules are broken down into sub modules and then designed. Like if we know we have to use an adder, full adder, either you write an equation and from the equation you take a gate, for the gate you design a transistor and do, or the other way is also, that is you use two half adders and start designing. So that is also possible. So that is, you have broken down the full adder module into half adder into half adder, and you're starting to design. So that is design hierarchy. Breaking down the modules into sub-modules, connecting them and getting the designs done is design hierarchy. Next is the design challenges or the physical design of FPGA. When we talk about physical design, once we know, we have already studied about the FPGA architecture, what it has a logic unit, a logical element, it has a IO block, input output block, and it has interconnects, how these blocks, various cells will be interconnected. Knowing all this, knowing what design, how, what are the components, we have to place these components and we have to connect them. So placement and routing is a very important aspect in designing. So it is like all that you place cannot be routed, and it doesn't give a proper output. Or else you cannot place everything haphazardly. It has to be placed properly, because the size, the delay, the heat dissipation, all that would have to be optimized. So that is placement and routing. That is, as I said, whenever we talk about placement and routing, the size comes into picture. You can place it haphazardly, but the size will increase. So in a given size, how effectively how you can place and how well you can route them so that the delay will be less, the power dissipation will be less, is very important. You shouldn't connect such that you get a very long delay. Or else when you're placing, you should know which component has to be connected. Those components to be connected, you cannot keep it at the either ends of the uh, uh, placement or of the chip, and while routing you have to connect from one end to another. That would cost you on the delay. So that things have to be taken care while doing placement and routing. So the first thing is placement. The separation of placement and routing arises an important problem. That is, it is a separate placement and routing would be a. So we'll have to look first place and then we have to route. And if it is not going to give an optimal result, again you have to replace and then reroute. And there are different algorithms for this. There are two types of placement, okay? That is bad placement and good placement. The length, looking into the length of the wire, suppose we are connecting two logical blocks, we have to look into the length of the wire for different cases, and whichever is giving a short length is considered as a good placement. And the length, that is it, the straight wires between the pins, the result is known as the rat's nest plot. The shortest length will be the rat's nest plot. The distance can also be measured using the Euclidean distance or Manhattan's distance. Okay, Euclidean distance will directly give you the distance between two logical units. Manhattan's distance is half, that is, it is roundabout distance. It will give you the roundabout distance. Placement approach, how placement can be done is, you have either by clustering or by partitioning. Clustering is considered to be bottom up and partitioning is top to down. Partitioning means you subdivide the nodes or modules or the system or the area, and you start designing. Clustering means the nodes are put together. As you go, every step you cluster or join the nodes and you get the final design. First algorithm or method is the mean cut method, placement by partitioning. Here you see this placement, and in this placement every time there is in every iteration you see it has been partitioned. You cut the module or you cut the layers. First you have the first whole layer, then it is divided into two, then it goes into four, so it goes on. Then each block or each module or each layer will be properly designed, then it will be connected. In that you correctly place in each cell or in each block, logical unit will be placed. How it will be placed, what work it will be done, that has to be decided properly. If you have to connect a mux and a adder together, you cannot keep it very far apart. It has to be placed one next to another. So you have to design those two blocks such that one becomes a mux, the other becomes an adder. So it will be continuously at each using iteration, every iteration you partition the module or the layer into sub-circuits, and those sub-circuits you design looking at how it has to be connected. Then the next and the other algorithm is Kernighan-Lin algorithm. It is a well-known partitioning algorithm. Its iterative tries to find and moves out of place element in the partition. If you look at this, the number of number of connections between two partition in the first case is 5. That is, you have B on partition A and A in the partition 2. The number of connections between these two partitions will be 5. And if you properly place A and B, that is, you shift the position of A and B, the number of connections between the two partitions reduces to 1. So it is out of place elements are correctly partitioned by using this algorithm. Next is cluster, that is placement used by clustering method. If you see here, in the previous case we had divided, whereas here now we go on joining the clusters or the sub-circuits together. Here in the first you see there is one node, in the next 2 nodes, and 3 in the third case 3. So the nodes are going on adding, it is clustering. This is clustering algorithm. Okay, next is the optimization technique, placement optimization technique, which is called this simulated annealing. Simulated annealing, it is an optimization technique, well-known optimization technique. It is a technique that tries a large number of changes to the candidate placement, which helps the algorithm avoid being trapped in local minima solution without reaching global minimum. Okay, usually we have seen annealing concept in metals. So the same concept is applied here, and then we get the optimum algorithm. This is an optimization technique. This place method is a iterative placement method. In each iteration, some logical elements may be moved based on the certain parameters by the annealing temperature. Exactly where a selected element moves to depends upon the details of the placement algorithm. It may occupy an area, or it may be temporarily allocated. That is, the element may be temporarily allocated some position. The new placement then evaluates whether this position is correct. The position occupied by this logical element is correct or it is not. Then if it is correct, it will retain. If not, again it will be replaced. Again it will be given some it can either be placed, and if it is not placed, fine. If it is placed, it will be temporary, where again it will check for all the constraints, whether all the constraints like delay, power, everything is optimized. If yes, that will be retained. If not, it will be again given some other position. So it is an iterative way of optimizing the placement. Next comes the routing. Okay, routing means selecting the proper path to connect the logical elements and IO pads. As I said, here there are two important things which we'll have to consider is the delay and the power dissipation. There are two types, that is global routing and detailed routing. In global routing, it is only showing you the general path, which blocks have to be connected. Detailed routing means it goes about the exact detail, whether you should give a horizontal line, vertical line, how many steps through or which blocks it has to move, the end, that is the two logical blocks, how they get connected from one end to another. It is a detailed routing method. Okay, again routing also, the wire length, the power dissipation, delay, everything has to be considered. The wire length is a very important resource which has to be considered. The length of the wire will increase the resistance, thereby the power heat, power dissipation. So then delay, everything will get uh, will uh, will be bad, and the design is not optimized if it is not properly routed. Global routing, uh, in this, as I said, it is just showing you which two blocks have to be connected, or it just tells these two blocks have to be connected. It doesn't show the exactly how they have to be connected, through which from which end to that, and how exactly it has to traverse through what route and come and get placed. It doesn't show that. It just shows that two blocks have to be connected. Okay, global routing is done to balance the requirements of various nets. Nets are routed one at a time, so the order in which the nets are routed affects the final result. A net may have one of the two problems. It may not be routable at all because there is no room available to make the connection, or it may take a path which gives too much delay. Okay, so there are usually, when you're routing, there are certain problems which you have, that is either it will give too much delay, or there is no connection at all among them. Okay, there are many ways to determine the order in which wires have to be connected or routed. Rig up and reroute is the simplest strategy for choosing the order in which the wires have to be connected, or the cells have to be connected. That is, if it doesn't optimize, reroute. Replace and reroute is one of the strategies which are used, simplest strategy which will be used. To optimize, again, as I said, routing with time information, delay plays a very important time. So the time driven FPGA routing has received much importance, so that the delay has to be minimized. So for this, there are different algorithms. Few of them we will discuss. The first one would be the maze routing algorithm. Okay, in this maze routing algorithm, the shortest path between 2 points is found. Once a wire segment is chosen for the path, both the ends of the wire segments are available for connections. FPGA interconnects can be modeled as a group whose edges are available. Wire segments and the nodes are connected between the wire segments. The job of the router is to find the best or the shortest connection between the nodes. And this is, and again, it can be an iterative, or as I said, rig up and reroute means it is usually an iterative process, and it has to be routed such that there is a shortest path, and it eliminates conditions in the routing. The next algorithm would be the Nair's algorithm. Here again, it is an iterative process. That is, it is using rig up and reroute concept. Okay, here the routing algorithm is designed based on congestion. In this algorithm, every net is rigged up and rerouted. It is rigged and rerouted. The first routing pass was used to estimate the congestion. The first time when you route, it will just look into the congestion, whether the signals are properly, whether it will be passed, whether the signals will be used by some other resources have to be used. So all these congestions, it will look into the congestion. The second routing pass used those estimated design details and redesign the wire to minimize the effect of congestion. What previous conditions, the details of previous conditions, initially first routing is done, it will take care of all the problems. Second time, considering the problems, uh, the routing is done so that the problems which were encountered in the first case will be minimized. So that is Nair's algorithm. Next is the algorithm that is called the Triptych algorithm. Triptych algorithm is an extension of Nair's algorithm. Again, it is an iterative process, that is rip and reroute process. Okay. In this, during earlier iteration, nets are allowed to share the routing resources with other nets. As the iteration process proceeds, the sharing of the routing resource is corrected. In this, the conditions are corrected as the routing resources will be corrected, increasing gradually with each iterations. The routing resources are corrected. After a large number of iterations, the net will negotiate among the congested resource to try and find a way to successfully route the circuit, allotting key resources to the net that need them the most. Here in the previous case, the the first problems were just studied, then taking care of the problems, the next time connections were done. In this case, the resources, every time they allot resource and see which components require the maximum, which path would take the maximum resource, and it was the resource was first prominence or importance were given to that allocation. By rerouting all the nets during each iterations, nets that do not absolutely require congested routing resource can be relocated. So this was about the this uh, routing technology, that is the Triptych router method. So with this we complete the fourth module. These are the questions which were seen in the previous exam question paper. I want you to answer these two, and in 2 days you have to submit the answers for this to the respective faculty in the Google Classroom. Now the questions I'll put up in the Google Classroom, but you answer and submit it. Okay, write it down and submit the same.